Welcome back to Mrs. Baker's quarantine lab. You can't be in school, but we can still do some science. What we're going to do is look at the rate of reaction of hydrochloric acid with magnesium ribbon. Any metal reacting with any acid is going to make a salt and hydrogen gas. So we're going to collect the hydrogen gas over time, and so we're going to see how much hydrogen gas is being produced every 20 seconds. In this case we're using hydrochloric acid, so we're going to make a chloride salt, so it'll be magnesium chloride. So how do we measure it? Well, the first thing that you need to do is set up your experiment. So I've got 50 centimeters cubed of acid measured out in a measuring cylinder. I'm going to pop that into a conical flask. I'm going to have at the ready a inverted measuring cylinder filled with water. So to keep the water inside, I'm going to invert it in my hand, and I'm going to just pop it under the water, and I'm going to make sure that I can see the gauge on the side. Now, of course, we're going to read the measuring cylinder upside down. When we produce the gas is going to bubble through the water, and it's going to displace the water back into the water trough. So we'll be able to measure how much gas we produce. To direct the gas to the water trough and into the measuring cylinder, I've got an angled delivery tube here. So I'm going to take about 3 pieces of magnesium. Remember, it's not important in this experiment to worry too much about measuring everything out accurately, because we're not looking at changing anything in our reaction. We're just going to use this to measure the rate of reaction. So we're not actually doing an experiment to change anything at the moment. So I've got 3 pieces of magnesium. I'm going to pop them into here, and we'll see what happens. In they go. I pop my measuring cylinder on. Make sure I put my bung on really tight. I'm going to pop my thing in there and press start straight away. So of course it's at 0 to start, and the rate of reaction proceeds quite quickly to start off with. Now play along at home and make sure that you pause the video and take the measurements as we go. So there's your first 20 seconds now. Take a measurement. There's another 10 seconds. It's proceeding quite quickly now. Okay, that's another 20 seconds. It's starting to slowly starting to slow down now. The rate of reaction is not going as quick. That's 60 seconds, you can take a measurement. It's definitely slowing. And we're going to keep going until we're getting no more bubbles being produced. There you go. I think our reaction has come to an end. We're going to run it to the next 20-second interval just to make sure that we get a nice flat line on our graph. So we're going to go to 1 minute and 40 seconds. There we go. So I can safely say we're not getting any more reaction. We're going to stop our stopwatch. Now, just for fun, say we wanted to test this gas to make sure that this gas was actually a hydrogen gas that we produce. We know it is because we know the chemistry, but we could also do a squeaky pop, which is fun. Should we go for it? Let's go for it. This should really be a lit splint, not a lighter. I do love a squeaky pop. Let's see how we go about graphing this result. So hi lovelies. What we're going to do now is assume that I've done that test 3 times. because of course I have. And we've now got 3 repeats. The reason why we take 3 repeats is so that we get a much more accurate result in the mean average, because then we can calculate this mean average. And if we did make a mistake, if we got a bad reading because of human error, for example, or we didn't put the bung on properly, there's lots of ways that human error could have affected our results. So if we do that, we can take out any anomalies, and then we can make sure that we're getting a more accurate result. So if we add up our things, let's take our 3 tests. We can do 23 plus 25 plus 26, and then we divide by however many data sets we've got, in this case 3. Then we end up with 24.6. Now, 24.6 is the mean average, but because our measuring device is only precise to 1 decimal place or no decimal places, then we can't go to 1 decimal place here. We have to round it. Our mean average result should be to the same level of precision as our recording device, our original recording device. So in this case, it's 0.6, so I'm going to round it up. So this is going to become 25. Now we're going to assume that we have done all of the mean averages, and now all we have to do is to insert our mean averages versus the time onto a graph. Okay, so the final thing left for us to do is to plot our results on a graph. I've just written our mean volume produced here so that I can plot it on the graph and I don't forget it. You can use your straightforward results table. The first thing that we're going to need to do is to draw our axis lines and decide our scale. So I'm going to look at the small numbers and decide what each one of them is going to be worth, because we need to make sure that every single small square on our graph has exactly the same numerical value for the axis that it's on. The 2 axes can be different, but they have to be the same along the axis. You can't do different kind of jumps, different number of jumps between, otherwise your graph doesn't work, obviously. So we're going to put time along the bottom in a rate of reaction graph. And of course, time always starts at 0. Always, 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 because there's no time elapsed when you first start your experiment. And then, because of the size of my graph, I'm going to decide that each one of these small squares is worth 5. So 5 seconds. So I'm going to go 5, 10, 15, 20, 5, 10, 15, 20, so that's 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, 100. So that's my bottom one done. I just need to put a title, time in seconds. All graphs must have a title and a unit for their axes. Then I'm going to go up the side and I'm going to plot my mean volume of hydrogen produced in centimeters cubed. So I'm going to go up the side, and for up the side, because of the size of my graph paper, I'm going to decide that each one of the small squares is worth 2 centimeters cubed. So I'm going to go 2, 4, 6, 8, 10, 2, 4, 6, 8, 20, 90, and my highest one is 93. 2, 4, 6, 8, 100. And then I'm going to draw my axis line all the way down. Of course, you're going to use a ruler and pencil, not a pen and freehand. Of course, the amount of products produced always starts at 0, 2. They like to ask you that in the exam. Why must your graph start at 0, 0? It must start at 0, 0 because there's no reactants and no time, no products produced and no time elapsed. So it must always start at 0, 0. Okay, let's have a look at plotting our data. Okay, so we've got 0, 0, we need a point there. 25 at 20 seconds, so we could just go 20, go up to 10, 20, and then 2, 4, 5. Let's plot our data point there. Remember, with your data points, they need to be big and bold. you will be getting marked in the exam on the size of your plot. Your examiner will want to know that your plot is exactly correct to within 1 millimetre. It doesn't mean that you have to do this. They don't have to be that big, but they do have to be big enough for the examiner to see it. And the X needs to be right where you want the point, right where it crosses. Here is right where you want the point to be. So 22 for 25. Okay, next comes 57. So at 40 centimetres, we've got 57. So I'm going to go up at 40 to 50, and then I'm going to count up 2, 4, 6, 7. So I want my X to be there. And this is why we use a pencil, so that we can rub out our dots. We don't want the examiner thinking that we meant to plot a point there. Then we've got 81. So at 60 seconds had elapsed, our mean average was 81. So when you're drawing your line of best fit, it's really important that you do a curved line, not a straight line. The reason being is we're going to use the slope of the graph to imply the rate of reaction. The steeper the graph, the faster the rate of reaction. The less steep the graph, the slower the reaction. So we can't just put our ruler on and draw a straight line. What we have to do is draw a curved line of best fit. The best way to draw a curved line of best fit is to just commit, get it done. This is why we do in pencil, because if we make a mistake, we can cross it out. We're going to just put our pencil on, and we're just going to make sure that we go through every single data point. And we've got a line of best fit there. It goes through every single data point, and you can see it levels off at the top. This is exactly how you draw a line of best fit and a rate of reaction graph. Hope that was helpful. Bye.